So the big idea here is today that in a Millikan apparatus, generally the oil droplets are suspended, which means that the forces are equal or balanced. Very similar to moving at a constant velocity back in the dynamics unit. So now what we're going to have is we're going to have the forces unbalanced. And so in fact you end up with a net force. And really, if you stop and think about it, you don't need to write this down, but if you stop and think about it, this is no different than objects that have an applied force Fa on them and the friction force, right? You add the two forces together, one's negative, you find the net force. It's all the same idea, except now it's what? Vertical, I think you mean. Right? It's now vertical. It's not friction, it's gravity and some sort of electric force, and the numbers are really weird. So that's, the only real difference. So in that sense, it's a good review. If you guys go back to test number 1, and I encourage you to do this, go back to test number 1 and look at some of those questions. I think you'll find them ridiculously easy. I'm hoping. How come? Because I'm doing the same thing over and over and sort of making them harder, right? Like add more weights to the barbell, right? If you go back to benching just the bar itself, you'll find it's pretty easy. Kind of the same principle. Okay, so let's begin here. So we got a 1.0 times 10 to the minus 4 kilogram object. It has a charge of 3.2 times 10 to the minus 19. It's dropped in electric field. The plates are 1.5 centimeters apart. And the electric field strength is 1 times 10 to the 15. And oh my gosh, all these numbers, I don't know what to do. How should I start this meeting? Make a list. I think what you mean is, you're a ventriloquist. Okay. So exciting. All right. I think whoever said that, what they mean, I think, is write down what you know. I think that's what you meant. Right? So the mass, how do I know this is the mass? Because the word mass doesn't even appear in there. So I'll see, how do I know that this number here is the mass? K says kg, well done. 1.0 times 10 to the minus 4 is the kilograms. A 1.0 times 10 to the minus 4 kilogram charge of 3.2 times 10 to the minus 19, so that is my Q. I'm hoping your instincts realize that that's how many elementary charges? 2. It's dropped into an electric field. The plates are 1.5 centimeters apart. What would you call that? The distance? Have we done anything with distance? Like displacement, have we done anything with that? Not recently. And it says determine the net force on the object. So are your sort of spider senses tingling and wondering, is that number sort of like those leftover screws when you get stuff from IKEA? They don't really do anything. They're just there to frustrate you. Like, what did I miss? And that's exactly what it is. In the teaching business, we call that a distractor. Doesn't mean nothing. The electric field strength. So what is that? That's the letter E. Electric field strength is the E. 1.0 times 10 to the 15. And we are to determine the net force. We have to determine the net force. Okay, let's make our little plan here. Let's draw a picture. What are the forces on this thing? Gravity and an electric force. Now, if there is a net force, then those forces are not going to be balanced, are they? They're not going to be equal. Do we know which one is bigger from the information? We don't know which one's bigger, so we can't really draw one bigger than the other. You think so?
Oh yeah. Look how small
It's a pretty small mass, but it's a pretty small charge too. But the electric field strength is giant. Okay, so we don't know. But how are we going to get our net force? Well, we need to find the Fe and the Fw. The Fw is easy. Mass times gravity. We have mass already. The Fe is the Q and the E, right? Together. So we just got to do those two one separately and then add them together. So there's your little plan. Find the weight force. Mass times gravity. 1.0 times 10 to the minus 4 times minus 9.8. Minus 9.8 times 10 to the minus 4. Now, is the negative sign here important? How do we know what's sort of the determining factor for when it's important? When there's sort of things opposite direction, like this is the force down, and we're going to have electric force up. That's positive, right? Can they both be positive? No, they have to be because they're opposite, right? It's when things are opposite that you have to worry about. So minus 9.8 times 10 to the minus 4 newtons. Now let's find the FE. Now, I've always written it, just don't write for a second. I've always written it like this. You might see on solutions, because we solve for F so often, is it okay if I just write it like this? FE is equal to Q times E. Can I write it like that? Okay? Maybe some of you have started doing that already. That's perfectly all right. Okay? All that is E equals F over Q. How do I get the F by itself? Multiply both sides by Q. So you get F equals Q times E. That's an E. That's an F. Okay? So F equals QE. You might see that in solutions because I did sort of do that for a while. So the Q is 3.2 times 10 to the minus 19. And I hope you did a little practicing yesterday with your calculator, your scientific notation. The E is 1.0 times 10 to the 15. So I get 3.2 times 10 to the minus 4. Now a little trick here, or a little sort of check. Should these exponents be in the same ballpark as each other? Like, if this is minus 4 and this was like plus 17, is that in the same ballpark? Like, this minus 4 would be 0.000098, and if this was 17, that'd be 320000000 trillions. Are they in the same ballpark? Not even close. These exponents here should be should either be equal or no more than 1 apart. Like if this one's minus 4, this one should be minus 5 or minus 4 or minus 3. How come? Well, these forces have to be relatively the same, right? One isn't going to be extremely larger than the other. They should be in the same sort of ballpark. So if they're not, you've likely made a bit of a mistake somewhere. Or perhaps I have. Okay, what's the next step? Do this. F net is equal to FE plus FW. Does it matter what order you put those in? The reason I put them in that order was likely because most people like the positive to be out front. Okay, so you add them together, and the overall net force minus 6.6 times 10 to the minus 4. What direction is that? Down. How do I know? Negative. So if I went back to draw my free body diagram, which one should be bigger? Could you now figure out what the acceleration of the object is? F net equals ma. Once you got the acceleration, then you go into kinematics for an A, where you got like initial velocity and how far does it go and time, all that awesome stuff. How much would that all be worth, do you think? I only see 3. Unless, of course, I said draw a picture. Is the picture necessary to this question? I don't think so. Is that hard, that one? If I'd shown you that back on February the 10th, you all would have ran for the door. Do you want to try this one? You have the ability to do it. Many of you. Do you want to try it? Do you want to do it on a loose leaf or whatever? It's up to you. Give it a try. I'm going to do my test. I'm going to give you 5 minutes to give it a try. If you can't do it, that's fine. Give it a try. Did you get those two things for your FW and your FE? Okay, now we need to find the net acceleration, so same as before. Now, what should be the acceleration? Ballpark. Like if there was no electric force, the weight force would drag down and the acceleration would be minus 9.8, right? So the FE is sort of acting like friction and reducing that. So your acceleration has to be something that's close to 9.8. Like if you got 4.7 times 10 to the 14, you got something wrong there. That's not going to be an acceleration. Meters per second squared. So far, so good, Josh? Yeah? Good? Yeah? Hey? Well, it says, how fast is it traveling after 1.5? So it's part of the question. Okay, so it's a part B, right? So how fast is it traveling after that? We're looking for the final velocity. You can only assume that the initial velocity is 0. So I'm going to write A equals delta V over delta T. This new acceleration is 3.26. The time is 1.5. So the change in velocity is minus 4.89. And since the initial velocity is 0, that means the final velocity is that number again. I heard someone say something about divide by 2. I think what they're talking about is this. Seriously, if I'd shown you this back in February, you guys would all quit. And how far will it have fallen? Yep, right back to the simplest thing. Ten marks? 1, 2, 3.
is that pretty much a complete review of the entire year? Pretty much. Well, like with the exception of vector addition and subtraction. Right, you are. I guess if I wanted to do that, Dan, it doesn't actually say it, but I guess if I were to do that, I could do like the FE is off to the side, right? Yeah, that's a great idea. My point is, if you can follow that and you can do that, you're going to be fine on the exam. Okay. Well, you know what? This worked pretty well. So I'm going to give you a chance to do number 3 on your own. I think number 3, there's space on the back, so if you need extra space, you can do that. No, I'm just saying that if you make a mistake, there's room for like, right? I've got it all in one page, my answer. So I'm going to say, you guys go ahead and try number 3. If you want to work with someone, do what you need to do to learn how to do it. Figure it out. It's not that bad. You can do it. We've got the mass, we've got the electric field strength, we're looking for the charge. This is actually more what Millikan was doing. Okay, so because we got the acceleration, the first step is to find the net force. 5.3 times 10 to the minus 6, and our acceleration is minus 2.3. Minus 1.219 times 10 to the minus 5 is my net force. Given the mass, we can find the weight force. There's our weight force. So now we're going to use this formula here to determine the FE. Okay, I'm hoping that the mathematics, the solving part, has become automatic for you. That minus 5.51.194 goes to the other side and becomes positive. I'm just going to flip it around. You should get an electric force of so there's your electric force. Now I'm going to write, I want to know the charge on the drop, right? Let's write it like this. E equals FE over Q. The electric field strength was 3.6 times 10 to the 6. Electric force is 3.975 times 10 to the minus 5. We're solving for Q. And you get a really big number. Well, sorry, not that, I guess, in coulombs. 1.1 times 10 to the minus 11. And then you have to convert that to elementary charges by dividing by 1.6 times 10 to the minus 19. And you get 6.9 times 10 to the 7 elementary charges. Now, is that a reasonable number? It's giant. You know, I can have that many elementary charges. And Alex, that's why I think I changed this number here, so you get a better number here. But then I think I forgot to change it on the student paper. So, how is that on a degree of difficulty? Easy, Renee? Wow. Okay, well that's good news. So you've got a few minutes left. You've got about 20 minutes or so left. You've got some practice problems there. You've got all day tomorrow. Use your time wisely. The time is starting to slip away. Time is key. Good luck.